So we're ready for the last talk of the session by Chenyuan, and it's going to be about white box fuzzing.
Thanks for the introduction. So, hello everyone, my name is Chenyuan, a PhD student from UIUC. Today I'm very excited to talk about our project, WhiteFox, white box compiler fuzzing empowered by large language models. Let me first go through some background knowledge about the deep learning system, which are the fundamental structure for all kinds of AI applications like ChatGPT or Copilot. It provides the fundamental support of safety, functionality, and user experience for the high-level AI applications. Thus, it's important to improve the correctness of the whole deep learning stack. Specifically, this work focuses on the deep learning compilers and optimizer. This is because the deep learning compiler or optimizer is a trend, as more and more deep learning compiler has been actively developed. The pipeline to use such compiler is like after the developers implement the model, they want to have a better performance during the training or inference. Thus, they choose those compiler with various optimization strategies to get an optimized model which has a greater performance. Due to the popularity and the importance, some work has been proposed to generate random models to test the whole process of this pipeline. However, they failed to cover the optimization strategies efficiently. Let me explain it with a motivating example. The left side shows the source code of the permute linear fusion optimization in PyTorch inductor, which will fuse the permute and linear operators when the permute operator only swaps the last two dimensions. Such triggering requirements are explicitly written in the source code. However, the random model generated by existing approaches, they rarely trigger this optimization. First, there are thousands of operators in PyTorch, thus it's pretty hard to just choose these two operators. Second, you also need to use the permute operators in a specific way that say only swap the last two dimensions. So, given the fact that such gray box or gray box fuzzing are not unaware of the source code implementation, they struggle with reaching such deep paths to trigger such optimization. As for the traditional white box fuzzing like symbolic or concurrent execution, the optimization strategies are too complicated and there are millions of lines in the compiler. Thus, it's impractical to model all the behaviors, and it also has the path exploration issue. So in this work, we have two insights. First, as I discussed, such triggering requirements are explicitly written in the source code. Second, the emerging larger models are good at comprehending code as it is trained on vast code data. Thus, in this work, we propose to combine the white box information and large language models. More specifically, we have an analysis agent which can analyze such source code information to infer the triggering requirements. And after that, a generation agent will be used to generate the test inputs following the requirements. We can see in this example, the model indeed has a permute and linear operators, and the permute only swaps the last two dimensions, which make it pass all the check and trigger this optimization. And it will help us to detect a previously unknown bug in it. Thus, we propose WhiteFox, which is the first white box compiler fuzzing empowered by large language models to fully test the optimization module in the modern compilers. The input to WhiteFox is the implementation source code of the target optimization. And as I mentioned, the first step is requirement summarization. An analysis agent will be used to analyze the source code and summarize the triggering requirements for the target optimization. And then a generation agent is used to generate various and diverse inputs following the requirements to trigger the optimization. And then we will compile and execute the test inputs to say whether it indeed triggers the optimization or whether it helps us to find a bug. If it indeed triggers the optimization, we will collect them and use as future example in the future generation. Let me talk about each component in more details one by one. So first is the requirement summarization. The task is to analyze the implementation source code of the optimization and infer the input pattern to trigger it. So thus we leverage a larger model-based analysis agent to summarize such pattern. So basically, the source code implementation is written in the low level, and we want the features of the high level input to the whole compiler. For example, the PyTorch model here for PyTorch inductor. And we also expect the larger model to summarize the requirement in a mixed format of pseudocode and natural language to have a better expressiveness and conciseness. And we will show the ablation study results for our design choice later. And after that, we will generate the various and diverse types following the requirements to trigger the target optimization. Similarly, we use another model-based generation agent with visual prompting to do this task. You can see that following the description, the agent is expected to generate a PyTorch model for this specific example. And after that, when the newly generated test indeed triggers the optimization, we will collect them and use them as a candidate fusion example for future test generation. So this is in this way we can enhance targeted guidance provided to the generation generation agent to generate more tests that could trigger the optimization. And additionally, we use some example selection algorithm to select the most effective candidates. And here is the implementation details of WhiteFox. We have 3 targeted deep learning compilers, which are PyTorch Inductor, TensorFlow XLA, and TensorFlow Lite. We collected the source code specific for optimization for each target, and the table shows the details about the number of the optimization collected for each deep learning compiler, and also what's their source language for their implementation. And as for the agent choice, we choose GPT-4 as an analysis agent and StarCoder 15B as a generation agent. And as for the budget, we have 2 settings. First is whether you use 24-hour fuzzing, and we also have our own setting for the ablation study. Let's say generate 1,000 tests for each optimization. And due to the time limit, I will mainly focus on the results on PyTorch Inductor. First is a comparison with the baselines. We can see that given the same time budget, let's say the 24-hour fuzzing, WhiteFox can cover 8 times more optimization than the state-of-the-art baselines, Titan Fuzz, which is a larger model-based model generator, and also the NSmith, which is a symbolic-based model generator. And we can also see that it has the most number of triggering tests that say it generates it has the most number of tests that could trigger at least 1 optimization. And it also has the best coverage performance. And here are the ablation study results to justify our design choice. First, as I mentioned, we use a mixed format of natural language and pseudocode for the requirement summarization. And here we will study, we have two variants. First is the natural language description only, and also the pseudocode description only. And we also have a variant that we skip such analysis process. I say we don't have any requirement summarization. We directly impose the implementation source code or optimization to the generation agent. We could say that the mixed format has the best performance compared to the single format and also the implementation source code only. And we also study by replacing GPT-4 with StarCoder as an analysis agent, and we indeed see a performance drop, which which shows that such tasks could require a powerful enough large language model like GPT-4. And we also did implementation study for the generation phase by disabling the feedback loop. And it turns out that the feedback loop helps us to achieve 2 times more triggering tests to boost the performance. And here is the bug detection results by WhiteFox for those 3 deep learning compilers. And in total, WhiteFox detects 101 bugs for deep learning compilers, and 95 are confirmed as previously unknown bugs, and 73 are already fixed. And we also contributed to 11 high priority bugs for PyTorch. And notably, only 12% of them can be triggered by can be detected by state-of-the-art baselines. And here is a bug example for the fused attention optimization, which designed for the attention mechanism, which is widely used in modern large language model. And the blue box shows the bug triggering test generated by WhiteFox. And we can see that after optimization, the output value of such model will have not a number, which is different from the output without any optimization. And such pattern is pretty hard to generate for those baselines because they don't have they are unaware of what is attention mechanism optimization and how to trigger it. And the right side shows the description generated by WhiteFox that help us to generate the test to find this bug. And here is another bug example for the linear ReLU optimization. Again, this is also very popular among the whole deep learning community. And we can see that first, after the optimization, the output value has negative value, which is totally unacceptable because the output domain of the ReLU operators is greater or equal than 0. And due to its popularity to use such linear ReLU pattern, the PyTorch developer label it as high priority. And with a similar pattern, when we feed the model with input tensor with bflow 16 data type, which is also commonly used nowadays to save the memory during the training or inference, the optimized model will just crash. And the reason is that this is due to a memory copy error, and the right side shows the code snippet to fix it. Overall, we propose WhiteFox, which is a white box compiler fuzzing bilateral models. It opens a new dimension of such white box compiler fuzzing by combining the white box information, let's say the source code, and with the potential of the large language model. WhiteFox is a dual agent framework. Let's say we have an analysis agent to summarize the triggering requirements based on the implementation source code, and then a generation agent is used to create numerous test inputs following the requirements to test the target optimization. In total, WhiteFox detected 101 bugs for PyTorch inductor, TensorFlow XLA, and TensorFlow Lite, with 95 confirmed and 73 already fixed. If you are interested, feel free to scan the QR code for the code repo and paper of WhiteFox. Thanks.
I can ask a couple of questions. So this is very impressive work. I mean, you found a lot of bugs. But so is there a way you can think of automating this pipeline for, like it feels like you have to do a lot of work on thinking about how to use the LLM for this particular type of code that is compilers. But it's like, it feels like there is a general abstract strategies that can be learned from here for essentially testing any type of code. Like what would be the, if tomorrow I have an application and I want to use your paradigm, how do you abstract that paradigm into something reusable?
Yeah, that's a very good question. So the reason we focus on optimization here, because in optimization implementation code, it has a relatively clear mapping from the high-level input, let's say the program to the optimizer, or to the program to the compiler, to the input to optimization implementation. So if your application has such clearly mapping that says the high-level input to your application and which is maybe similar to the input to the function you want to test, then I think our framework can be directly used. Otherwise, maybe you can have some mapping inference first that say what would be the mapping from the high-level input to your application to the function you want to test, and then you can apply it similarly.
Hi, thanks for the talk. On an earlier slide, you mentioned that you try to get the LLM to generate like diverse inputs. Was there like a particular strategy you used for that, or like a way of kind of measuring whether the generated programs were diverse, or was it kind of instructing the LLM in a specific way?
Yes, that's a very good question. So basically, we just use some prompting. We just use the instruction to guide the language model. Let's say don't generate the similar tests we already generated, and also be as creative as possible. And to measure the diversity, we indeed show some coverage results in our paper to show that with such things, with the feedback loop, the coverage improves. I mean, just use the same prompt. Yeah.
All right, thanks.
So you had this slide comparing your work to NN Smith and the other one about the number of optimizations covered. Yeah, the triggered ones. Were TitanFuzz and NN Smith? I think they were targeting ML compose, but they weren't specifically targeting optimizations, right?
For the TitanFuzz, yes, they are not specifically targeting the optimization, but they generate such random models that could be used for optimization testing.
Did the baselines cover other behaviors that WhiteFox doesn't? Like in terms of optimizations, clearly WhiteFox does better, but I'm just curious whether the other tools were complementary in testing on some other dimensions.
I can explain it more. For NN Smith, it try to generate a valid model that say they don't want the model to be invalid due to some parameter setting, for example, the parameter to the convolution. So that's the main goal of the NN Smith. But our work will not ensure the validity of the model. That say our model could be invalid, but they can still be used for testing. And for TitanFuzz, they mainly they mainly use. They just want to show that the larger model are zero-shot fuzzers that say they can generate such models with a relatively good pass rate, that's a relatively good valid rate, and they just generate the models and test it without such optimization oracle. They use the oracle as the CPU-GPU comparison and also the automatic differentiation oracle. So basically, I think our approach, WhiteFox, can cover them. Yeah.
Okay, thanks.
Okay, I think that ends the machine learning for code session. So let's thank the last speaker.